Welcome to lecture 6. I trust that you are doing fine. And, you are able to review the last lecture. If you recall, in the last lecture, we discussed about sample size, determination, and hypothesis testing. In that lecture, we look at how to determine appropriate sample size for your study, and how you can calculate sample size for both population means and proportions. We also discuss fundamental concepts of hypothesis testing, including null and alternative hypotheses. In that lecture, we were able to differentiate between errors in hypothesis testing. Specifically, we discussed about type 1 and type 2 errors, and the concept of p-value, and how you can arrive at decision regarding your null hypothesis, either by using the p-value or use the critical values. So we consider a number of real-world problems in that lecture. Today, our focus will be on hypothesis testing for population parameters with large samples. So we also look into hypothesis testing for means and proportions when sample sizes are large. We will also explore testing, how we can test the difference between two means, and also the difference between two proportions. We will consider practical examples to solidify our understanding. Hopefully, at the end of the lecture, I expect that you have a good understanding of the framework for hypothesis testing with large samples, and two, you will be able to differentiate between testing population means and proportions. Three, you will be able to conduct tests for differences between two means and two proportions, and apply hypothesis testing concepts to real-world scenarios. So these objectives will guide us through the session as we build on our statistical inference toolkit. As usual, let's warm up with a few, just 5 pre-lecture multiple choice questions. I believe those questions will stimulate our interest and also prepare us for the uh, the the issues and concepts that we hope to cover in this lecture. So let's start with this first one, which I believe everyone should be able to answer. So, what is the primary goal of hypothesis testing? A, to prove the null hypothesis is true. B, to make an inference about a population parameter using sample data. C, to calculate the population mean exactly. D, to avoid all errors in statistical analysis. Uh, type your option, type your choice. Uh, yeah, yes, I can see Joy, Tawoka, Abayomi. They've made their choices. Sheriff Dean, that's good. Are there more choices coming? I believe if you have been going through you know, uh, the lectures and the course textbook, you shouldn't be finding uh, this question to be difficult. Okay, so let's see what the true answer is. The correct answer is B. Hypothesis testing is used to make inferences about population parameters based on sample data. Uh, we've said this is it's not about proving the null hypothesis. It's not about uh, calculating any population quantity. It's also not about uh, avoiding all errors in statistical analysis, but is about drawing inference about the population using sample data. The second question is this: what is the significance level in hypothesis testing? What is the significance level in hypothesis testing? A, the probability of rejecting the null hypothesis when it is true. B, the probability of failing to reject the null hypothesis when it is false. C, the sample size used in the test. D, the standard error of the test statistic. Uh, I, I hope you are able to make the right choice this time around. What are the options? Bayomi is going for A. Wuraola is going for A. Emmanuel Banwo is going for A. Ikman is going for A. Okay, but Samiat is going for B. Samiat, maybe you need to check uh, your choice again. Uh, So let's see what the correct option is. Is A. Quite a lot of you got that correctly. Um, the significance level, which is alpha, is uh, the probability of type 1 error, of committing type 1 error, which is, in other words, is the likelihood of making a type 1 error. And type 1 error is the error of rejecting uh, a correct hypothesis, rejecting the null hypothesis when it is correct. Okay, so the third question is, what does a two-tailed test evaluate? You recall we talk about one-tail and two-tailed test. So what does a two-tailed test evaluate? A, whether a parameter is greater than a certain value. B, whether a parameter is less than a certain value. C, whether a parameter is different from a certain value. D, whether a parameter equals to a certain value. What are the options? What are the options? Well, I can see Joy, see Temitope, see Joshua, see Wuraola, see, yeah, maybe Blessing is up. Taoka, see. Okay, I think this consensus is around C. Well, you are correct. So, uh, a two-tailed test checks for differences in either direction from a specified value. So when you say it's greater, it is directional. When you say it's less, it's directional. But in a two-tailed test, uh, it could be either, either uh, way, whether greater, no. So it's directionless, so to say. Uh, Great. Question 4. What condition is typically required for large sample hypothesis testing? What condition? Because our lecture today will focus on large sample. Uh, no. So under what condition do we uh, uh, re do we require large sample hypothesis testing? A, sample size n greater than 1,000. B, the sampling distribution approximate normality. C, the population mean is unknown. D, the sample mean equals the population mean. So what are your preferences now? Abraham say 4, Tawuka B, Idris A. No, Idris is still discussing question. So for Abraham B, Lasisi B, that's good, but no consensus as such. Blessing A, Franklin B, Semiat B. Okay, so let's see what the correct answer is. The correct answer is actually B. So uh, the central limit theorem ensures that the sampling distribution approximates normality for large sample. We trashed this uh, the discussion on central limit theorem extensively. So it's about the distribution of the approximation of the sampling distribution to normality. So the the correct answer in this case is B. Now the last question for the pre-lecture quiz is, what is the purpose of a p-value in hypothesis testing? What is the purpose of a p-value in hypothesis testing? A, to provide the critical value for the test. B, to measure the probability of observing the sample data under the null hypothesis. C, to replace the null hypothesis with the alternative hypothesis. D, to determine the sample size required for the test. So, what is your choice? No. What is your choice? I can see Joshua A, Sheriff Dean A, Mutia A, Emmanuel B. Okay, so there is also no consensus. Even Wuraola is saying D. Hickman is insisting on A. So what is the correct answer in this case? B. So the p-value quantifies the evidence against the null hypothesis by measuring the likelihood of the observed data under the null hypothesis. So it measures the weight of the evidence in your data against the null hypothesis. That's what, so you can on the basis of the p-value take a decision whether the null hypothesis should be rejected or should not be rejected. So let's go straight to what we have today. Remember that the discussion is going to center on hypothesis testing for population parameters with large samples. And you already know, we will know that hypothesis testing is a systematic way to evaluate claims about population parameters using sample data. So in hypothesis testing, the researcher makes a claim and then collect data and then use test statistics and from the test statistics obtain the critical value, the p-value, and then be able to determine whether the weight of evidence in that data in the sample is strong enough to reject the hypothesis. So hypothesis testing is a systematic procedure. It's not it's not one that is based on one's opinion or based on feelings or based on tradition. It is a scientific process of evaluating weight of making a claim and testing, whether that claim is valid or not, or whether that claim is true or not. So, but we've discussed all of that before, but the concern now is about large samples. So we are focusing on large sample um, in hypothesis testing. Large samples allow us to apply the central limit theorem, which we've talked about. The central limit theorem ensures the sampling distribution approximates to normal distribution. And this makes hypothesis testing with large sample more robust and reliable. So we use statistics, that is the standard normal distribution for this test. So anytime we talk about large sample, the test statistic that we'll be using is the Z, uh, the Z statistic. So the that Z statistic assumes that the sample size is large enough for the normal approximation to hold. So uh, there are five important steps that we must always follow anytime we are testing hypothesis. So the first one is that of uh, stating the hypothesis or formulating the hypothesis. And this involves two things: specifying the uh, the 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 null hypothesis, stating the null hypothesis, um, stating the null hypothesis and the alternative hypothesis. So sorry. So stating the null hypothesis and stating the alternative hypothesis, the two of them must be stated very clearly, and uh, they they are complements. So one is a complement of the other. Then the second step is to choose the significance level. So the significance level, which is your alpha level, or which is your type 1, the likelihood of committing type 1 error. Uh, that uh, alpha level is usually very small uh, because you don't even want to, if possible, you don't want to reject um, a correct hypothesis. That's why you make it so small. So so the usual value, we've mentioned that before, could be 0.01, 0.05, or at best 0.1. The third step is to compute the test statistic. That is the Z for large sample. The Z statistic I will show you shortly. So the Z statistic, the formula depends on whether uh, you are computing for the mean, or you are computing for the proportion, or you are computing for the differences between two means, or differences between two proportions. So you will see the formula when we know in subsequent slides. The fourth step is to now determine the critical value or the p-value. As I said, these values, these two quantities, you could use any of them. The critical value or the p-value, they only help you to arrive at a decision regarding your null hypothesis. So that that you have to determine those values before you can uh, take a decision regarding your null hypothesis. And in step 5, that is where the decision is now taken here. So uh, if the absolute value of the critical value that you have is greater, no, if the computed, the absolute value of the computed no, uh, uh, z no, is greater or equals to the critical value, then you reject the null hypothesis. Otherwise, you do not reject. So if you go by the p-value, again, you reject if the p-value is uh, smaller than uh, the alpha value. So if the p-value is smaller, so if you go by the p-value, if the p-value is less or equals to the alpha value, then you reject. Otherwise, you accept the null hypothesis. So you are making decision based on the null hypothesis, because when you reject the null hypothesis, then of course you accept the alternative. So let's start with the hypothesis testing when you are dealing with population mean. So when you are dealing with population mean, you have H naught, and then you have mu equals to mu naught versus the alternative, which is mu is not equals to mu naught. This is mu. So um, here mu naught is a specified value. Mu naught is a specified value. Sorry, this this thing is yeah. So this is mu. So the mu naught here could be any value that is specified. Could be any value that is specified. So you recall that the first step is to formulate the hypothesis. So once the hypothesis is formulated, then the next step is to specify the level of set the significance level, whether 0.01, 0.05, or 0.1. The third step is where we are now, which is the test statistic. So for this hypothesis regarding a population mean, the test statistics is given as is the Z, so which is the standard normal uh, Z statistic. So X bar is the sample mean. That is the mean obtained from the sample. The mu naught is the hypothesized population mean. So that represents maybe the value the researcher is claiming. So and then and that's the value that is here. That's the value that is mu naught here. That this value. So this is the value that is in the formula. And then the denominator, if you recall, this denominator represents the standard error. The standard error of the mean. So you recall that is the sigma there is the population standard deviation, which is the value that captures the population variability, and then the n there is the sample size. So the expression sigma over root of n is the standard error. The standard error. So this formula is used for testing a population mean. For testing a population mean. So let's look at an example again. So in this example one, a factory claims the average weight of a product is 500 grams. So that is the claim about the product, emanating from the factory. So you could regard that as the population mean of the average weight of products coming from the factory. And to test whether this claim is true or not, a sample of 100 products were drawn randomly. So, and then the average, that's the sample mean of the 100 products is given there as 495 gram. The sigma, which represents the population standard deviation, in this case it is known, so is given as 20 grams. So the alpha that is chosen for this test is 0.05. So for us to take a decision whether this claim is true or not, we have all the information. So the hypothesis can be specified as H naught mu equals to 500 gram versus H1 mu not equals to 500 gram. So that is the first step. Specify the hypothesis, specify the null, and also specify the alternative. That is now specified. And then 2, you have to choose the level of significance. That is, you have to choose a value that will represent the likelihood of committing type 1 error, which is alpha. And here we've been given that value to be 0.05. So the third step is to calculate the Z statistics. Remember, the Z statistics is the X bar minus the hypothesized value over sigma over root of n. So that is the formula for the Z statistics. So if you substitute, this is the average from the sample. This is the hypothesized value, 500 gram. This is the standard deviation, the population standard deviation, which is the 20 gram, and then 100 that represent the sample size. So your Z value is minus 2.5, minus 2.5. So so in this case, you now have to use your alpha to determine what the critical value is. And we've discussed how you will get the critical value in the table. Good enough, when your alpha, if you recall, when your alpha is 0.05, your level of significance is 0.05, then the critical value is 1.96. The critical value is 1.96. So, so with that, remember that this hypothesis is a two-stage test because it is directionless. It's not saying that it is greater or it is less. So we are dealing with a two-stage test. So that is why our critical value will have to be plus or minus 1.96. We're actually interested in the absolute value. So if you go back to the expression given here. So we can simply look at the absolute value of the of the critical value. So which is 1.96. So now that uh, uh, if we compare the 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 value that we have there with if we compare Z and the critical value, you will now see that Z is less than minus 1.96. If you also use the so it falls into the rejection region. That's the uh, that's the that's the point. So we have to reject the null hypothesis in this case. So which means we reject the hypothesis that, or the claim that the average weight of the product is 500 gram. So the conclusion here is that based on information in the sample, uh, that claim, the data does not, the evidence in the data does not support that claim. Uh, so that's but it doesn't tell us whether it is less or it is more. But the conclusion is that it is not equal. So we reject the null in this case. So how then do we also go about hypothesis testing for population proportion? So in this case, I said earlier that the formula for the Z statistic will vary depending on whether you are dealing with mean, or you are dealing with proportion, or you are dealing with difference of means, or you are dealing with difference of proportions. So we've seen when you are dealing with a single population mean and the sample is large enough. So now we want to look at population proportion. So this is the formula where Z is this, is the Z statistic, and the P hat is the sample proportion, and then the P naught is the hypothesized, or the proportion that is being claimed by the researcher. So every other thing they are straightforward. In the denominator, you have the square root of the uh, the 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 proportion being claimed in the population, and then the uh, the complement of it, which is 1 minus the proportion all over n. So that gives you again the square root of that expression. This expression here is the standard error for the sampling distribution of population of proportion, the sampling distribution of sample proportion. So if you are to implement this, as usual, you need to one, state the hypothesis, compute the Z statistic. No, but even before then, you have to choose your alpha level, compute your Z statistic, determine the critical value or the p-value, make a decision, based on your alpha value. You can see that your alpha value is very important. And interestingly, you are the one that will choose that alpha value. But uh, the, the standard procedure is that you should choose the value before you collect the data. So not to abuse the process, you have to choose the value before you collect the data. But those who abuse, usually they collect the data, compute the Z before now they decide which alpha value to use. So let's take example regarding testing for population proportion. So in this example, we consider a survey report, that the survey that reports that 60% of voters support a policy. So, and to be to to validate or at least test whether this claim in the report uh, is you know is uh, is true as far as the population is concerned or not, then a sample of 400 voters were randomly drawn from that, and then was found that out of the 400 voters, only 220 support the policy, which translates to uh, estimated sample proportion of 0.05. Just a minute. So that translates uh, to sample proportion of 0.55, and the uh, alpha level, that is the type 1, the likelihood of committing type 1 error is 5%. So we can now compute the Z based on formula the formula that we have here. So the this is the estimated proportion from the sample, proportion of voters in the sample that support the policy. And this is the claim, that is 0.6. That is the claim uh, in the survey report. And this is P naught. This is the 1 minus P naught. So uh, you have that, and this is the sample size, which is 400 voters selected. So evaluating this gives you minus 2.04. Again, this is a two-chain hypothesis. Therefore, so the critical value for alpha equals to 0.05, then level of significance is 0.05, then the critical value for the set is 1.96. So if you compare the value with the z, the computed z minus 2.04 is less than minus 1.96. Again, in this case, we get the in other words, the claim in the report that 60% of voters support the policy is rejected based on the evidence in the sample. So the evidence in the sample is not strong enough to support the claim in this report. So that is when we are testing for single population, for one population. So giving example involving population mean, giving example involving population proportion. Now we are going to look at how we test the difference between two population means. Sometimes you have two populations, and you want to compare the two populations. For instance, if you have two groups, group A, you have another group, group B, then you want to, this is a population, this is also another population, and you want to compare these two groups. So in comparing these two groups, you want to test somebody is saying that you can't hear me. Okay, maybe let me reload this. Let me try to reload. Just keep your yes, let me know if you are able to hear me very well now. Let me me know if you are able to hear me. Are you able to hear me? Very well. Are you able to hear me? Very well. So what is the are you able to hear me? Let me know if you can hear me. I can't hear you. Wow. Are you able to hear me now? I'm not sure it's a network problem. You can hear me very well now. There is still noise in the background. I can't hear you. Where could that noise be coming from? Let me know if we are trying to put everything in place. Let me know if you are able to hear me now. Hello? Are you hearing me? Are you hearing me? Huh? Yeah, you have noise at the back. Wuraola said he's not able to hear. Are you able to hear now? Still no, only slightly. Where is the problem coming? Where is the problem coming from? What about now? What about now? Huh? Are you able to follow? Audio is cracking. Yeah. What's causing this? I suspect what could, well, I can't even imagine. I can hear you partially, sir. I think it will pick up maybe the battery. Uh, the battery went down, so I needed to. Okay, are you able to hear now? I can hear you partially. Let me know if we have first moved away from partial level to full level. It has improved. Tawoka, thank you for that information. Thank you for that information. Any other feedback? Any other feedback? I want to get more feedback. Yeah, so okay, I think it is a bit better now. Emmanuel, thank you for that. It is clear now. Peter, thank you. Thea, thank you. It's okay now. Thank you. So let's continue from where we stopped. Sorry for, thank you for that. So let me go back to the lecture. Let's go back to the so just a minute. Fine. Uh, I don't know if you can see my screen now. I don't know if you can see my screen. It appears you are not able to see the screen. Okay, just a minute, I will settle that. Uh, yeah, have to. Okay, so you will see it now. I think you should be able to see my screen now. Thank you for your patience. You should be able to see my screen now. Uh, yeah. Are you able to see my screen now? Are you able to see my screen? Yeah. Are you able to see my screen? Okay, great. So, uh, thank you very much. So, uh, before the interruption, we were talking about having two populations, population A and then population B. And we want to compare the two populations. Uh, maybe population A could be those who smoke, population B could be those who don't smoke, or population A could be uh, uh, those in a particular community, and B could be those in another community. So uh, sometimes we want to compare whether the two populations are the same or not in terms of certain characteristics. Maybe it could be uh, maybe um, measurable quantity. Uh, so if we have class A, class B, we may want to say whether the performance, average performance in the two classes, uh, whether they are the same or not. So we usually have this kind of situation in real life. We want to compare performance in class A with performance in class B. So we look at average performance in A and compare it with the average performance in B. So uh, anytime we are testing the difference between two population means, so we will expect this population to have its own mean, which is mu1. This population also will have its own population mean, which is mu2. This population will also have its own population variance, and this one also will have its own population variance. Uh, and then what we do is we take sample from this population A, so that sample is small n1. Again, we take sample from this population, that is n2. So we get the mean from the first population, that is x bar 1, and then we get the mean from the second population, that is x bar 2. So we get the mean from that, so the x bar 2. So with this, we can now test whether these uh, two populations, whether they are the same or not. So, but the requirement, the assumption is that one, uh, the samples are large and they are also independent. So, in other words, we expect the sample size to be for the sample type from the two populations N1 and N2 to be greater or equals to 30. That's when we say the sample size is large. In statistics, large samples start from anything greater than 30. Another assumption before we can use this test is that the variances of the two populations are equal. So that is sigma square 1 is assumed to be equals to sigma square 2. That is the variance of the first population is equals to the variance of the second population. This second assumption usually it may be very difficult. You even have to test it, but we are not going. So for now, we are only assuming that they are equal. So the requirement for using Z statistic is based on these two assumptions: large independent samples and equal variances. Equal variances is what we call homoscedasticity in, but that you will not need to worry yourself about. You will learn about equal variances and unequal variances. So the formula now for the statistics is what you see here. And the formula says that this sample mean from population 1 minus the sample mean from population 2, divided by what you see here is the, if you recall, this is the standard error of the difference of the sampling, the standard error of the difference of the sampling distribution of two means, or two populations, of two means. So, and that is the variance of the square root of the sum of what you have here. So this is the variance of the population 1, and the sample from the population 1 plus the variance of the population 2 divided by the sample size from the population 2. So let's take example to be able to apply this this formula. So in this example, a company wants to compare the average productivity of workers in 2 different locations. Workers that are in location A, so you have some workers in location A, and then workers in location B. And these workers, so they represent those in location A, those in location B. The company is interested in comparing the average productivity of the 2 groups. So what the company did was to take sample from workers in each location. So a sample of 30 is taken from location A, and then the average productivity is 52. The population, this is the population standard deviation of course, once you know the standard deviation, you can get the variance, and if you know the variance, you can get the standard deviation. So the population standard deviation for the for location A is 10, and for location B, the sample drawn is 35, and the mean productivity for location B is 48, and the population standard deviation is 12. So the company wants to test whether productivity levels are significantly different at alpha level of 0.05. So that 0.05 is the level of significance. That is the likelihood of rejecting the null hypothesis when it is true. So the hypothesis is set up. That is the first step. We have to set up the hypothesis. So the hypothesis is that the mean of population 1 is equal to the mean of population 2. That is, productivity in location A is the same as productivity in location B. But in this case, you could also rewrite this. So this also implies that there is no difference. That is, location A minus location B, in terms of productivity, the difference is 0. So if this hypothesis could be written also this way. So if you say they are the same, that's okay. If you also say the difference is equals to 0, you are still saying the same thing. So you could write the hypothesis in terms of the difference being 0 and the difference not being 0. So, or you simply say the productivity, average productivity in location A is the same as average productivity in location B. So, whichever you are on course, and therefore that is the first step. You have properly formulated the hypothesis. So the null hypothesis is no difference in productivity. The alternative is saying there is difference in productivity. So we have to now compute the said statistic. Of course, you know that this one will be 0, and we have the values for the so this we have the values for the sample, the sample, the average productivity from location A. This is the average productivity from location B. So this is the formula. So if you also, since this will be 0, that's why the formula earlier is simply saying x bar. That's why the formula is simply saying x bar x bar 1 minus x bar 2, everything all over whatever you have there over the standard error. So so since H naught assumes no difference, then the mu1 minus mu2 will be equals to 0, and then the formula reduces to this. So we can substitute the values. Maybe we start getting the result for the denominator, that is the denominator that gives you the expression you have. So the standard error is actually 2.73, and then you can now compute the set, which is x bar 1 minus x bar 2, which is 52 minus 48 over the standard error, and then you have the final value to be 1.47. So as usual, if your alpha value is 0.05, the critical value will be 1.96. And this is a two-stage test, so we can consider plus or minus. So now we can take a decision, because our Z is 1.47, and this is less than 1.96. So since it's less, so our Z is less than the Z alpha. So since this is less, we fail to reject the null hypothesis, which simply means that the data, the evidence in the data is not strong enough to reject the null hypothesis. In fact, the evidence in the data overwhelmingly supported the null hypothesis. So we fail to reject the null hypothesis, which in this case simply means that there is no significant difference in productivity between the two locations at the 5% level of significance. You will notice that it's always proper you indicate the level of significance you are reporting, in your your decision, your conclusion, so that we know that that decision is based on uh, uh, the 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 choice, or is based on the fact that uh, your likelihood of rejecting the the null hypothesis when it is correct is 5%. So, which means you are 95% confident about the decision that you have taken. So let's look at the proportion. Just like we have uh, uh, difference, just like we can test the difference between two means, we could also test difference between two proportions. So you could also have population A and you have population B, and you are comparing proportions from the two populations. So you may say proportion in population A is not different from the proportion in B. You will see example now. So, but as before, the assumption is that unlike in the mean, you have two assumptions. They also apply here. The samples are large and independent. You take large enough samples from the two populations, that is N1, N2 must be greater or equals to 30. And then, so this is the expression you use to compute your Z statistic. So this is your P hat 1 is the proportion. So you know here you have your sample, proportion. You also have your sample proportion. You have your N1 and you also have your N2 and so on. So you can easily substitute in this expression. So this is P1 is the sample proportion in population 1. P2 is sample proportion from population 2. N1 is sample size drawn from population 1. N2 is sample size drawn from population 2. So, but take note of this P. This P here, you will notice, does not have it doesn't have the subscript. So this P is what we call the pooled proportion, and is computed by adding how many successes do you have, how many successes do you have in population, in sample 1, how many successes do you have in sample 2. So that is what gives you this expression. So X1 is the number of successes in population in sample 1. And then N2, X2 rather, is the number of successes in sample 2. N1 is the sample size drawn from sample 1. N2 is the sample size drawn from sample 2. And so this pooled proportion is what you now use here. So it is not, it is not from any of them, but it is a pooled one. So let's take example regarding testing the difference between two proportions. We have a scenario here in which the researcher wants to compare the success rates of two marketing companies. You have two marketing companies, so you have A, you have B. So campaign A, you have also campaign B. And then the proportion of the proportion of successes, there are actually 120 successes out of 200. Maybe this company A, draw out of a sample of 200, that 200 potential customers that the campaign, they were able to campaign to. Only 120 eventually accepted. So that represents the number of successes. Again, for company B, a sample of 150, only 75 succeeded in accepting the campaign. So P1 is 0.6, P2 is 0.5. So precisely half of those campaign to accepted or joined this accepted the service. So the test is this level of significance is 0.05. Like I said, you could use 0.01, 0.05, 0.1. So again, the starting point is to formulate the hypothesis. So in this case, this is also saying there is no difference in the success rate. So that is the success rate from campaign A, marketing campaign A is not different from the success rate for marketing campaign B. The alternative is saying the difference is not equals to 0, which implies that there is a difference. It implies that there is a difference. So we can now compute our test statistic using the formula. But before you do that, you have to get the pooled proportion. The pooled proportion, that is the sum of successes from the two, 120 plus 75, divided by the sum of the samples from the two, which is what you have here. And so the pooled proportion is 0.557. That is the pool proportion. So you can now substitute that value here. And then, of course, you know the sample size. P1, P2 are the respective sample proportions. So the denominator gives you 0.0537. That's the standard error. And then you can now compute the Z statistics by getting the numerator P1 minus P2, and also you arrive, that leads you to 1.86. And then since your alpha is 0.05, as usual, your critical value is plus or minus 1.96. You have to take a decision now. And so our Z is 1.86. Our critical value is 1.96. So since it's a two-tailed test, so we can focus on the positive side. So since our Z value, Z calculated or computed Z value or computed Z statistic does not exceed the critical value, so we fail to reject the null hypothesis. And again, what that means is that the evidence in the data overwhelmingly supported the claim in the null hypothesis. So there is therefore no significant difference in success rate between the market A and market B at 5% significance level. So this is how we reach decision, and this is the scientific procedure for arriving at decision, whether in science, social science, engineering, any discipline for that matter. This is the scientific process. Remember, the focus is on large sample, and we have consistently used the Z statistic. Even so, anytime we are dealing with large sample, that is the appropriate statistic to use. So, in summary, large sample hypothesis testing uses the Z statistics, and that's what I do. And whether you are dealing with the means, I told you earlier, you deal with the means when you are dealing with quantitative measures. You use the proportion when you are dealing with qualitative measures, which is based on looking for units with certain attributes. So when you get the attributes, then you are successful. So you have you regard that as a success. So 2, the Z statistics is used because of the fact that the sampling distribution of the mean, of the proportion, of the difference of they tend to normal distribution, which is what the central limit theorem claims. So the sampling distribution tends to for the mean, proportion, the difference of two means, the difference of the sampling distribution tends to have a normal shape. So as the sample size gets larger. So that's the central limit theorem. So it is because of this theorem that we use the Z statistic. So large samples ensure that we have reliable approximations to normality. Then remember that you must properly, correctly define your null and alternative if you want to get valid results. And you don't specify your hypothesis after you have collected data. You have to, your research, you have to start with the hypothesis. Then you choose your level of significance, alpha. Then you collect the data, and then you now calculate the test statistic. And then you compute the test statistic, and you also get the critical values or the p-values before you now compare the computed Z and the critical value that you have or that you have obtained, which is actually, which depends on your level of significance, and you take a decision. So the decisions are based on critical values or p-values. You can go either way, you get the same results. So this is the end of the class, but as usual, we will have to do, we have 5 post lecture questions to help us review what we have learned so far. So I hope you are ready. Let me know if you are ready. Type yes if you are ready. Pamela has even started. Some people have started. Ogunshola. Are you or have you? This is post lecture quiz. So question 1, what's your choice? A hypothesis test for the mean of a population assumes what? A, the sample mean equals the population mean. B, the population distribution is normal or N is large. C, the sample size is always greater than 500. And D, the population standard deviation is unknown. Hypothesis test for the mean of a population assumes, what are the assumptions? What are the assumptions? So we've mentioned that. Yes, I can see people making good judgment from this question. Excellent, Nigeria Teslimot, Oladipupo, Samiat. Okay, so what is the correct answer? B. Large sample sizes or normal population distributions are fundamental assumptions for large sample hypothesis testing. Question 2, you have to do a bit of thinking here. If your null hypothesis states that the population mean is equals to 100 and you choose your level of significance to be 0.05, what does alpha represent? What does alpha represent? A, the sample mean. B, the standard error. C, the probability of a type 1 error. D, the p-value of the test. Everybody should get this. Everybody should get this. Abayomi says C. Emmanuel C. Shemilore, Nigeria. Okay. Oh, that's interesting. That's some of you follow the lecture. That's good. That's good. That's good. So the correct answer is C. Alpha is the probability of rejecting the null when it is actually true, also known as type 1 error. And you must always choose your alpha before you even collect the data. So it is the second thing after formulating the hypothesis. And you always want that alpha that you are choosing to be small, to be as small as possible, because you don't want to reject your null when it is actually true. You don't want. So you want the likelihood of rejecting it to be so small. To be so small. That's why the highest or the highest commonly chosen is 0.1, which translates to 90% confidence. So, number 3, what is the formula for the Z-test statistic for a population proportion? Not difference now, for a population proportion. You can see the formula yourself. A, you can see for B, for C, we are talking here about population proportion, population proportion, population proportion, population proportion. What's your final choice? What's your choice for question 3? What's your choice for question 3? Emmanuel says A. Emmanuel says A. Emmanuel says A. Emmanuel, you need to watch that formula carefully. Emmanuel, you need to watch that formula. Yeah, you need to watch. Everybody. So Oladipupo says B. You have to watch. Oladipupo, you have to watch that formula very carefully. Very carefully. Yeah. I think the consensus is around A, except Oladipupo now that is moving away from others. Simi is choosing B, C. If I'm oh, okay. Okay, so let's see the correct answer in this case is A. So yeah, those who chose A are correct. The formula is used to test hypotheses about population proportions. Question 4. If the p-value of a test is 0.03 and the alpha, that's the level of significance, is 0.05, what will be your decision? The p-value is 0.03 and your alpha is 0.05. What is your decision? You will reject H naught, that's A. Fail to reject H naught, that's B. Increase alpha, C. Reduce the sample size, D. Everybody should be able to get this. So what is your decision? Let me see. 4 people are saying, Ladi people chose B. Wow. People, Franklin chose B. Nigeria at B. Semia A. Okay, B. Wow. Wow. Blessing A. Similore A. Nasisi A. Yeah, Emmanuel. Those of you who have B, you have to have a rethink. You have to have a rethink if you have chosen B. So the correct answer is A. So you will have to reject the null hypothesis because you have to compare the p-value. If the p-value is less or equals to the chosen alpha, remember you are the one that chose the alpha level. So the p-value is coming from your data. It summarizes the evidence in your data. And if that evidence, if the p-value is less or equals to alpha, it simply means that the evidence in the data does not support the claim in the null hypothesis. Finally, this is the last question. For 2 sample means, X bar, so you have 2 populations. The mean from population 1 is 52, the mean from population 2 is 50, and then sample size from population 1 is 30, from population 2 is 40. The standard deviation for the 2 populations are given as 8 and 10 respectively. What is the formula for the Z-test statistic? What is the formula for the Z-test statistic? Since we are talking of mean here, so you have to look at that, look at it very carefully. Look at it very carefully. So, what are your choices? What are your choices? What people are going for A. So there's a consensus. There's a consensus. So the correct answer is A. This formula calculates the Z statistics for testing the difference between 2 means with known standard deviation. So, gentlemen and ladies, this is the end of the class for today. I should congratulate you for being part of this class, and also being very active in the class. We are taking note of those who are very active in the class. So continue to prepare yourself ahead of the class, and also follow keenly uh, the class. If you have other questions, feel free to meet other colleagues and also attend the practical class. Uh, I can't see any question for me to answer, or any comment. So thank you very much. Enjoy the rest of your day. See you next week.